I feel like we've all gotten pretty comfortable with the parlor tricks of modern AI.
Oh,
Like
definitely.
you ask it to summarize a 50-page PDF and it just spits out a bulleted list in, what, 3 seconds?
Yeah. Or you tell it to write a polite but firm email to your landlord.
Right. And it does a shockingly good job. It feels like we all have this helpful, maybe slightly overly enthusiastic intern living in our browsers.
Which is great for productivity, sure.
Yeah. But today, for our deep dive, we're looking at a new piece of foundational research that, frankly, completely changes the threat landscape.
It really does. It's a massive leap.
Because we're talking about an AI that does something much more intimidating. We're talking about autonomous hacking.
Right, and not just running a few automated scripts that a human wrote beforehand.
Exactly. Genuinely teaching itself how to break into systems from scratch.
Yeah, we're moving away from that realm of assistance, where the AI just generates text or code for a human to use. We're moving into the realm of autonomous exploitation. This is an AI acting as a continuous, self-improving, offensive security agent.
Which is just wild to think about. And that brings us to the source material on our desk today.
Yeah, the launch safe paper.
Right. It's a fascinating and, well, sobering new research paper by Praneeth Narasetti and Shivanajendra Babukore over at LaunchSafe.
And they built this system, right?
They did. They built an AI system called Mako. And our mission today is to break down exactly how this thing works.
How an AI literally writes its own hacking tools on the fly.
Exactly. And also why, counterintuitively, the absolute hardest targets are suddenly the fastest for it to break.
That part is still blowing my mind, honestly.
It's crazy. And, what all of this means for the future of cybersecurity for all of us.
Well, the architecture behind Mako is really the engine of this entire conversation, right?
Yeah, let's start there. What makes it different?
So the authors classify Mako as a new breed of AI. They call it a self-evolving agentic operating system, or an SE-AOS.
SE-AOS.
Yeah, and the self-evolving part is really what separates it from the chatbots you use every day.
Because most AI agents right now, they're frozen, right?
Exactly. The model is trained. The developers give it a static set of tools, maybe like a web search tool or a calculator.
Right.
And it just applies those frozen capabilities to whatever prompt you give it. It can't learn new tricks on its own.
Okay, so previously I might have thought of a normal AI like a Swiss Army knife.
That's a good way to look at it.
Right. It comes with a blade and some scissors, but if you need a screwdriver, you're just out of luck.
Yeah, you can't use what you don't have.
But that analogy doesn't really capture the mechanism of what Mako is doing at all. From reading the paper, it feels much more like a biological immune system.
Oh, I like that analogy.
Yeah, because if a normal AI encounters a problem it doesn't have a tool for, it just fails. It stops.
Right.
But Mako is like an immune system that encounters a totally novel, unknown virus. It doesn't just give up.
No, it adapts.
Exactly. It analyzes the protein structure of the virus, synthesizes a brand new, custom-built antibody to dismantle it, and then remembers how to make that antibody forever. Or, sticking to the knife analogy, it's like a Swiss Army knife that realizes it needs a screwdriver, melts down some scrap metal, forges the screwdriver, and just adds it to its own handle in real time.
That captures the dynamic perfectly, especially the synthesis part.
Yeah.
In the paper, Narasetti and Corey explain that Mako's architecture is divided into two distinct loops that are constantly running.
Okay, 2 loops. Break those down for me.
First, you have the reasoning loop. They compare this to the user space in a computer operating system.
So this is like the front-facing part.
Right. This is where the AI perceives a target, forms a hypothesis about how to break in, and grabs a tool from its current library to try and pick the lock.
Okay, so the reasoning loop is the attacker at the front door trying different keys.
Exactly.
But what happens when the key breaks in the lock? When it just doesn't work?
Well, that's where the second loop kicks in. They call this the capability evolution loop.
The capability evolution loop.
Yeah, and it acts as the system's kernel. This is the core innovation of the whole paper.
Why is it so innovative?
Because when the reasoning loop tries an exploit and fails, Mako doesn't just mindlessly guess again or, hallucinate a success.
Right.
It takes the raw error logs from that failed attack, reads through the failure trace, and actually diagnoses the root cause.
Wow.
And then it uses its underlying large language model to actually write brand new Python code for a custom exploit capability.
Wait, let me stop you there. Because the mechanics of this are just wild. It's writing its own exploit code.
From scratch, yes.
But how does it know the code it just hallucinated actually works before it tries to use it on the live target.
Well, it doesn't just guess. That would be too messy.
So what does it do?
Mako takes that newly synthesized Python code and compiles it inside a localized, safe sandbox environment.
Oh, so it has like a little testing ground.
Exactly. It tests the new tool against a simulated version of the target's parameters.
And if it fails in the sandbox?
If the tool fails in the sandbox, Mako just reads the new error logs, tweaks its own code, and tries again.
That is terrifyingly efficient.
It really is. And once the tool successfully works in the sandbox, Mako hotloads that new capability directly into its own live tool library.
Just plugs it right in.
Yep. Gives it a description and makes it immediately available to the reasoning loop.
So the AI is treating its actual exploit capabilities as a mutable, versioned kernel that grows at runtime.
You nailed it.
I mean, it's literally expanding its own brain based on what it learns from its failure.
Right. And the authors make a really compelling argument here. They suggest the security industry has been looking at autonomous exploitation all wrong.
How so?
We've spent years trying to make the AI's reasoning brain smarter, right? Trying to make it, quote-unquote, think better.
Like giving it a higher IQ.
Exactly. But Mako proves that capability, the actual actionable tools in the library, is what truly matters.
So it's not about being a genius, it's about having the right tools.
Right. They are turning the concept of the capability into a self-extending, verified kernel.
Okay, I have to jump in here, though, and be the skeptic for a second.
Please do.
Because, we've all been burned by AI before.
Oh, absolutely.
Large language models hallucinate. They are notorious for just confidently delivering absolute nonsense.
Oh, yeah, they'll make up anything.
Right. An AI will look you straight in the eye, so to speak, and tell you the capital of France is Berlin, or make up a legal precedent that never existed.
True.
So if Mako is running this massive automated loop and spits out a log saying, mission accomplished, I hacked the server, how on earth do we know it actually did?
That's a great question.
Like, couldn't it just be self-reporting a success without actually finding a real vulnerability?
So that is a critical vulnerability in AI research generally, and it's one the authors set out to eliminate entirely here.
Okay, how did they do that?
They dedicate a significant portion of this paper to proving that Mako isn't just hallucinating its way to a passing grade.
Right.
To do this, they subjected the system to what they call a fabrication-proof verification regime.
Fabrication-proof, that's a strong claim.
It is. They tested it against a benchmark suite known as XBOW 104.
Right, the XBOW 104 validation benchmarks. In the source material, they describe this as a set of 104 containerized web applications built like a capture the flag competition.
Exactly.
And they span 26 different vulnerability classes. But before we get into the results, let's ground this for you listening.
Good idea.
The paper mentions classes like cross-site scripting, SQL injection, insecure deserialization. What are we actually talking about here?
Let's translate those into practical terms. So a SQL injection, for example, is when an attacker tricks a backend database into spilling sensitive information it shouldn't, like user passwords.
Okay, classic database attack.
Right. And cross-site scripting, or XSS, involves injecting malicious scripts into a trusted website so that when you, the user, visit it, your browser unknowingly executes the code.
Yikes. Okay.
Yeah. And insecure deserialization is essentially tricking an application into unpacking a malicious package of data, thinking it's totally safe.
So these aren't just trivial little bugs.
No, not at all. These are complex, enterprise-grade vulnerabilities spread across multiple difficulty tiers.
Okay, so we have 104 distinct apps with these nasty vulnerabilities hidden inside them. How did LaunchSafe make the test fabrication-proof?
Through a really brilliant cryptographic mechanism.
I love a good cryptographic mechanism.
Right. So every single time one of these 104 target applications is spun up for Mako to attack, the testing environment plants a cryptographically fresh, completely randomized 128-bit flag deep inside the app's protected data.
A 128-bit flag.
Yeah, the flag looks like the word flag followed by a massive string of random alphanumeric characters.
Which means this string of characters doesn't exist anywhere in Mako's training data. It literally didn't exist 10 seconds before the test started. It changes every single time the container runs.
That's the beauty of it. So to prove that Mako successfully hacked the app, it is not enough for the AI to just output a text summary claiming victory.
It can't just say, I did it.
No. The ground truth testing harness scans Mako's raw tool output. The absolute only way Mako gets credit for a successful solve is if its exploit forces the target application to literally spit out that exact brand new 128-bit flag.
The math on an AI faking that is just staggering.
Oh, it's impossible.
Right. The paper points out that the chance of the AI just randomly guessing that 128-bit string is 1 in 2 to the power of 128.
Which is practically zero.
Right. It's a mathematical impossibility. Mako can't talk its way into a passing grade. It has to deliver undeniable cryptographic proof.
Which is what makes the headline result of this paper so significant.
Drumroll, please.
Under this unforgiving fabrication-proof regime, Mako achieved full suite coverage, a 100% success rate.
100%.
It autonomously drove every single one of the 104 targets to emit that randomized flag. 104 out of 104 benchmarks completely verified.
Okay, let's take a breath and just think about the implications of 100% success rate.
It's a lot to take in.
Because if you have a system that can flawlessly execute 104 different hacks, the next logical question for anyone paying attention to cybersecurity is, well, what are the economics?
Right. How much did it cost?
Yeah. How much server time, how much compute is it taking to pull this off? Because if it costs $1 million in supercomputer time to crack one app, we're safe for a while.
Yeah, that would be a nice comfort. But let's look at the compute economics the authors actually laid out.
Okay, lay it on me.
The entire 104 benchmark campaign processed roughly 1.03 billion tokens.
Wow, billion with a B.
Yeah. And a fascinating detail is that about 95% of those were input tokens.
Because Mako is constantly rereading its own massive, growing library of tools to figure out what to do next.
Correct. And that tool library hit around 180 custom tools by the end, by the way.
That is insane.
Yeah. So they ran this architecture primarily on Google Gemini 2.5 Flash, which is highly efficient.
Okay.
And it only dynamically escalated to Gemini 3.1 Pro when the reasoning loop got stuck and needed heavier cognitive power.
Smart.
Now, considering the scale and the 100% success rate, what do you think the total API cost was for this entire campaign?
I mean, I read the number in the paper and I still can barely believe it.
Say it for everyone else.
It was $478.99.
Yep. Under $500.
That is the total API spend at official Google list pricing to hack 104 separate verified applications.
That was wild.
If you do the math, that breaks down to roughly $4.61 per benchmark to autonomously generate a verified exploit.
Let's let that sink in.
Seriously, let's put that in perspective for you listening. Think about the web portal you use to pay your rent, or, I don't know, the HR software your company uses to manage payroll.
Right.
Mako is proving that the complex vulnerabilities hidden in those kinds of systems can be mapped, diagnosed, and flawlessly exploited for less than the cost of your morning latte.
Yeah. The barrier to entry for mass exploitation just hit rock bottom.
It really did. But the cost is alarming, sure. Yet, what is perhaps even more counterintuitive is how the system actually spent those API calls.
The turn economics.
Right, because when the researchers analyzed the data, they discovered something that challenges a core assumption about how hacking works. They call it the level 3 inversion.
Let's unpack that because it's a huge finding.
Yeah, because my assumption going in was simple. If a target is categorized as a hard or level 3 difficulty vulnerability, it should take the AI way longer to crack than a simple level 1 challenge.
That makes sense, right?
Yeah, you'd think the AI would have to sit there spinning its wheels, running hundreds of attempts, trying endless combinations before it finally cracks the hard stuff.
That is the logical assumption. But the data showed the exact opposite.
The exact opposite.
Yeah. The researchers looked at the turn economics, meaning how many back-and-forth actions or API calls Mako had to take to solve a target.
Okay.
For the entire suite of 104 challenges, the median turns to solve was 7.
Which, by the way, 7 attempts to break an app is already blistering fast.
It is. But for the absolute hardest challenges in the suite, those level 3 targets, the median was only 2 turns.
Wait, 2 turns?
Yes, 2.
That means 1 turn to select and execute the exploit and 1 turn to report the flag. It's essentially a one-shot kill on the hardest targets.
Exactly.
How is that even possible? Why does the hardest stuff take the least amount of effort?
The researchers summarize this phenomenon with a powerful phrase. They say, capability, not reasoning, is all you need.
Capability, not reasoning. Okay.
We tend to anthropomorphize AI, right? Think about what makes a hack difficult for a human.
Well, a human hacker has to hold a massive amount of context in their head.
Right.
They have to manually test edge cases, write custom scripts, and painstakingly chain tiny, seemingly unrelated flaws together.
Exactly. It's cognitively exhausting.
Right. The human brain gets tired.
But Mako doesn't experience cognitive load in that way. For Mako, once its evolution loop synthesizes a specific capability, and that tool exists in its library with a clear, keyword-rich description, the difficulty entirely collapses.
Oh, I see.
The AI doesn't have to quote-unquote think hard. It just matches the target's profile to the perfect tool it already built.
Let's make this concrete, because the paper highlights a very specific case study that perfectly illustrates this.
Yes, the XPN-066 benchmark.
Right, XPN-066. This is categorized as a Level 3 highly complex vulnerability known as HTTP request smuggling.
Request smuggling is notoriously tricky.
Yeah.
The architecture in this specific challenge involves a lenient front-end proxy server sitting in front of a very strict back-end server.
Okay.
And hidden safely behind that strict back-end is an internal virtual host that holds the cryptographic flag.
So it's double layered.
Yes. And crucially, that internal host is not meant to be reachable from the outside world at all.
Okay, so let's use an analogy here to break down the mechanics of request smuggling. Imagine a very exclusive club. You've got the front door bouncer, that's the lenient front-end proxy.
Right, he's pretty relaxed.
Yeah. And deeper inside, you have the VIP room bouncer, that's the strict back-end server.
And the flag is sitting in the VIP room.
Exactly. A classic attack fails because the front door bouncer checks your ID, normalizes your request, and says, you're just a regular guest. You can't go to the VIP room.
That's a great way to visualize it. So how does Mako bypass them?
Right.
Operating in its reasoning loop, Mako realizes that the front door bouncer and the VIP bouncer are actually disagreeing on how to read a very specific, maliciously malformed piece of ID.
A malformed HTTP header.
Exactly. The front door bouncer looks at the bad ID, ignores the weird part, and silently lets the request through.
Because he's lenient.
Right. But the strict VIP bouncer looks at that exact same ID, rejects a piece of it, and processes the rest of the data as a brand new, separate request.
Oh.
Yeah.
This desynchronizes the two bouncers. So Mako figures out that because the two bouncers aren't communicating properly, it can attach a hidden VIP pass to the back of a regular ticket.
Precisely.
The front bouncer lets it in thinking it's just one normal guy, but the VIP bouncer gets confused, splits the ticket in two, and processes the smuggled VIP pass, routing the attacker right into the hidden internal server.
Now, for a human hacker, discovering that exact parser discrepancy between two specific servers and handcrafting the wire-level HTTP payload to exploit it, it's a massive time-consuming headache.
It requires deep, deep expertise.
It does. But Mako's capability evolution loop generalized this parser discrepancy detection into a reusable tool.
Right.
It wrote a Python script specifically designed to test for and exploit this kind of request smuggling. And once that shiny new tool was compiled and sitting in Mako's kernel,
Difficulty just vanished.
totally gone.
Mako saw the target, selected its new request smuggling tool on turn 1, executed it, and grabbed the flag, solved in 2 turns.
That is the core thesis of the Level 3 inversion.
It's mind-blowing.
The difficulty of a hack doesn't live in the AI's quote-unquote brain or its reasoning capacity. The difficulty lives entirely in the tool library.
Right.
If the capability is missing, the AI fails. If the capability exists and is easily discoverable, well, the hardest, most complex hacks in the world become a single $5 API call.
Which brings us to the elephant in the room.
I was wondering when we'd get to this.
Because if LaunchSafe has built a system that can reliably turn the phrase, here is a URL, into a working, verified exploit at machine speed across all sorts of vulnerability classes, why isn't the internet currently on fire?
That is the million-dollar question.
And more importantly, as I was reading through this paper, I noticed a very glaring omission.
No GitHub link.
Exactly. There is no GitHub link. You can't just go download Mako's code.
The authors did that very intentionally, and they dedicate a significant portion of their introduction to addressing why.
Right, the dual-use dilemma.
Yeah, it falls under the umbrella of dual-use research of concern. This refers to technologies or findings that have clear, highly beneficial defensive applications, like helping companies patch their software.
Sure.
But they could also be catastrophic if used maliciously by threat actors.
We are talking about an automated, self-improving hacking engine. That is the definition of dual use.
Exactly how the authors view it.
Yeah.
And just to impartially report on their stance here, they made a deliberate, calculated choice to withhold the operational payloads, the actual exploit chains, and the source code for Mako's tool library.
Yeah.
They explicitly state in the paper, quote, "We publish the science we withhold the weapon.
We publish the science, we withhold the weapon. It's a striking line.
It really is.
But it makes perfect sense when you consider how the cybersecurity ecosystem currently functions.
It does. The authors explain that the primary barrier protecting most of the web today isn't that software bugs are unknown.
Right. Security professionals know the vulnerabilities are out there.
Exactly. The real barrier is that reliably chaining together the reconnaissance, the discovery, the exploitation, and the verification of those bugs still takes highly skilled, manual human effort.
Right.
It takes a hacker sitting at a keyboard doing the work, which means it doesn't scale infinitely.
Human effort is the bottleneck.
Yes.
But Mako removes that human bottleneck entirely. It reduces full-spectrum web exploitation to a repeatable, automated pipeline.
And that is exactly why they won't release the code.
Makes sense.
The authors argue that handing this autonomous pipeline out to the public in a ready-to-run form wouldn't just be a neat educational tool for network defenders.
Oh, no.
It would act as a massive force multiplier for mass exploitation.
Yeah, it would give anyone, regardless of their skill level, the ability to launch highly sophisticated, customized attacks at machine speed.
Right.
So they're publishing the architectural blueprint. They want the world to understand the concept of the self-evolving Agentic OS. They want other researchers to see the fabrication-proof testing methodology, the staggering economics, and the proof that the level 3 inversion exists.
They're laying out the facts.
They are waving a flag saying, this is what is coming. But they're keeping the actual loaded gun locked in the safe.
They're proving that the underlying physics of cybersecurity have fundamentally changed without accidentally arming malicious actors.
Right.
They want the security community to scrutinize the architecture and understand that capability-driven AI is the new frontier of offensive security.
So to summarize our deep dive today, we started by looking at a major shift in artificial intelligence.
An AI that doesn't just generate polite emails, but actively writes its own hacking tools.
Exactly. We explored Mako, a self-evolving agentic operating system that uses a two-loop architecture.
Right, the reasoning and evolution loops.
Yeah, when it fails, it reads the error logs, writes custom Python code, tests it in a sandbox, and hot loads new exploit capabilities into its own kernel.
And we saw how the researchers proved this wasn't just AI hallucination by using a brilliant 128-bit cryptographic flag system,
Right.
achieving a flawless, verified 100% success rate on a major security benchmark.
And we unpacked the stunning economics. Mako can autonomously verify and exploit enterprise-grade vulnerabilities for roughly $4.60 a target.
Which is incredibly cheap.
So cheap. We also learned about the level 3 inversion, the counterintuitive reality that once an AI synthesizes a tool for a complex problem, the difficulty of that problem collapses to a mere 2 turns.
A single API call, essentially.
Right. And all of this led to a stark warning about dual-use technology and why giving away the source code to an automated hacking pipeline is simply too dangerous for the current state of the internet.
We are definitely witnessing a paradigm shift.
Big time.
The era of humans using tools to hack is transitioning to an era where AI agents build the tools to hack themselves.
Which leaves us with a final lingering question to ponder as we wrap up.
What's that?
Well, if offensive AI like Mako can autonomously diagnose its own failures, synthesize code, hot-load new capabilities, and adapt to targets at machine speed for a few dollars, what happens when defensive cybersecurity systems start self-evolving in the exact same way?
Oh, wow.
Right. Are we looking at a future where AI attackers and AI defenders are locked in an invisible microsecond-to-microsecond arms race?
Just battling it out on their own.
Exactly. A world where they are rewriting their own code and throwing newly forged tools at each other faster than human comprehension while we just sit back and watch.
That's a chilling thought.
The digital landscape is evolving itself, and the murky waters are getting deeper. Thank you for joining us on this deep dive. Keep questioning the consensus, keep looking at the data, and we'll catch you on the next one.